Okay, sac135 problem number 4. This first part, I want the energy Q that would have to flow into this rod to increase the temperature by 2 degrees. Well, we'll just use our relation, essentially a definition of specific heat. C is equal to mc, or Cm delta T, where delta T is given as 2 Celsius degrees, and C, I think, is given. It looks like everything's given. Density is there. Specific heat capacity, that's what we need right there. So 377 joules per kilogram Celsius degree times the mass given as a kilogram, and then times delta T, which is 2.00 Celsius degrees. Let's see, 2 times 7, it just turns out to be 2 times 377. 2 sevens is 14, 2 sevens is 14, carry the 1, that's 15, 2 threes is 6, carry the 1, that's 754 joules. Alrighty, so we can plug that in there. And then the distance that one would have to lift the rod to do an amount of work on the rod equal to the amount of energy there. So this is like review of old stuff. That was part A. Part B, the work I would have to do is given as what we just found, 754 joules. And the work I would have to do would be equal to the negative of the work done by gravity and lifting that thing up, and the gravitational force of the Earth, which is the negative of the change in potential energy, the gravitational potential energy. In other words, it's just the change in the gravitational potential energy, which is the final value of potential energy minus the initial. So I better get a before and after picture here. I'll establish a reference level. Let's say in the before picture, my object is at the reference level. In the after picture, it's a height h above the reference level. Initially, it's got a speed of 0, and finally, it's got a speed of 0. So, let's see. Initial potential energy is 0 by inspection. Final potential energy will just be mgh, so I got the work is equal to mgh, which it was 1 kilogram. I think it might have been given to 3 sig figs, but newtons per kilogram for a gravitational force constant. And then the h, oh, we're solving for the h. Okay, forget that. Actually, I think I'll knock that out. Solve for the h here. Just w, script w over mg. Be a little ludicrous to have that with a regular W, where the regular W is the symbol we use to represent weight, and mg is the weight on the bottom. That would just be 1. But this is work up top with the script W and mg on the bottom. And what did we find? 754, I think, 754 joules. .00. How many sig figs did they give? Yeah, it was 4 sig figs, 3 zeros. Kilograms, 9.80 newtons per kilogram. Kilograms cancel. A joule is a newton meter. So the newtons will cancel, and we are left with meters, which is good for an H. So we got 754 divided by 1 times 9.8, so just divided by 9.8. So I got 76.9 to 3 sig figs meters. Got a 1 kilogram chunk of brass. I could let it sit in the sun, let it warm up by 2 degrees Celsius, and the amount of energy increase that it experienced would be the same as the amount of energy increase it would experience if I lifted it roughly 80 meters, which is about 240 feet, which if I got 12 feet to a story would be about 20 stories. Lifting that thing up 20 stories would correspond to the amount of energy that goes into it when you just warm it up by 2 Celsius degrees. So interesting. 76.9 meters is how high I would have to lift it up, and then see how fast would it have to be moving for it to have that amount of kinetic energy, which was 754 joules. So part C, I got a kinetic energy of 754 joules. Kinetic energy is 1/2 mv squared, v being the speed, so v 2k, multiply both sides by 2, divide both sides by m, and then take the square root. And I got it's equal to 2 times the 754 joules divided by 1.000 kilograms. This is a Newton meter, which is kilogram meter per second squared times meters, or kilograms meters squared per second squared. The kilograms cancel out, and I'm left with meters squared per second squared under the radical, which yields meters per second for the final result, which is a good thing because it's supposed to be a speed. So let's see if I can substitute those values in. I got square root. I think what I'll do is put the stuff inside the square root. It's 2 times 754 divided by 1, which is just the same thing as 2 times 754. Put that inside the parentheses. Select it and double click on the parentheses there, and then take the square root of all of it by raising it. Oh, there's the square root. I'll go ahead and put the square root in front of that, and then have to delete the extra parentheses. Hit enter, and I get 38.8. Call it 38.8 to 3 sig figs. 38.8 meters per second. You know, if I wanted to get that in miles per hour, I would multiply by a mile over 1,600 meters. And I want to get rid of the seconds, so 3,600 seconds to an hour. That's roughly a factor of 2. Call it doubling that, so be talking like 80 miles an hour. Rough ballpark. We don't need to calculate it, but rough ballpark, 80 miles an hour. So I don't think anybody could throw the thing that fast, but a kilogram object going at 80 miles an hour would have a kinetic energy equivalent to the thermal kinetic energy, internal kinetic energy it would have if it was the amount of energy it would take to increase its temperature by 2 Celsius degrees. That's pretty amazing, I think. Okay, that should do it for SAC 135, problem number 4.